So I have a research paper in which we need to understand this is the paper depth anything 3 version, and let's understand this paper is about what. So I will create a new notebook and let's paste the link. I can paste as many as your URLs. Let's analyze it. The agents will analyze it. Let's explore the others option what we have, like audio overview. It's like a podcast. Video overview, like one person will explain the slides. And mind map, yes, it will be like a web like thing. Everything will be attached to see. Report, it will generate the report based on our sources. Flashcards, like our questions and answer like cards. And quiz, we know. Infographic will be an image which like a notebook, a note, one page note which contain image. And slide desk, like a beautiful PPT containing pictures and explanations. So here it has given the explanation, and let's ask for audio overview, and it's generating. And let's see the video overview, and I'm very interesting about the infographic and slide deck. So it has generated the performance and the infographic. Let's see that. Okay, so let's understand. I also don't know about this, what is depth anything 3. So I know about depth anything 2 version. It's like a depth map. If you give a single image, it will generate the 3D view of that image. Yep, we can't see the behind of the object also, like whatever there in the image stuff, it will get into 3D. So let's understand this together. Depth anything 3, reconstructing our world from any view. Okay, and new foundation model from the by Dan Seed, achieving state-of-the-art 3D geometry reconstruction with the simplified unified transformer architecture, a unified minimalist approach. Okay, any number of image, we can have the same objects image, I think at different angles or different image. Single plane transformer, Dino V2 backbone, no complex architecture modification. Okay, then predicts depth and the ray maps from any view. Okay, it's give the depth for the each of these pixels, and consistent depth and camera ray map. What is camera ray map? Let's understand this. Can't we ask questions? Here is the option. What is camera ray map? Let's see what it will give. Okay, our podcast is ready. We'll listen. Camera ray map, often referred to simple as the ray map, is a crucial component of the geometric reconstruction formulation used by the model like a depth anything V3. And the ray map provides a dense per pixel presentation of camera pose and the direction of the light ray and editing from the camera origin. Okay, depth map is like how far the pixel is from the camera view, and this ray map provides the position for that pixels. Okay, great. So let's see the infographic. Wait a second, this is not this one. Okay, so then teacher model is there, then student model, trained with a teacher student model. Teacher uses synthetic data to create a high quality labels for the real world training data. Okay, they are using real world training data as a teacher. Okay, so teacher model uses the synthetic data to create a high quality labels for the real world training data. Okay, I didn't get that. Can I copy this? You can ask the LLM what is this student model, teacher model, student teacher model. We can ask like what is this student TEA teacher model. Teacher student model or the teacher student learning paradigm is a training methodology utilized in the depth anything V2 and related depth estimation models to unify diverse training data and generate high quality supervision. So purpose and the context, can I write a explain in simple way? So I understand that what is this teacher student learning model means that the data which they have is very noisy, and this is also very real world data, and it is very noisy. If they directly give to the student model, it will train on base that only. So if we give image, it will give a noisy output. So what they have done that, so if they give image and student model will generate the very noisy image, means pixels, most of the pixels will out of their alignment. So what they have done, they made a teacher model in which they have trained it more with higher benchmarks, means making him master in the synthetic data. They have used synthetic data like 3D models in the generated in the computer, and by that the teacher model get prepared in which it doesn't have any noisy data. Then student model learn from the synthetic data and noisy data with the help of teacher model. Teacher will like size, I think, can punish when student model goes wrong, so that student model de-evaluate its parameter. So here comes the previous SOTA VGGT. Let's see. Pose accuracy, scan net plus. Okay. Reconstruction accuracy. Okay. This is the pose and reconstruction accuracy thing. Setting a new standard in the performance, outperforms previous state of the arts, surpassed the prior leading model VGGT in the both pose and accuracy. Okay, they have surpassed it, and they are telling that they have got a higher accuracy than the depth anything version 2 from a single image. Okay, and then depth anything 3 produce cleaner, more detailed construction, geometric, regular, and less noisy point clouds. Nice. Pose accuracy has increased, and the reconstruction accuracy has also increased. Cool. So this is the thing, good content, and we can let's listen to the podcast.
And the challenges are just immense. Things like monocular depth, how far is everything in a single photo, or structure from motion, where you rebuild a 3D scene just by moving a camera around.
And then there's SLAM, putting it all together for things like self-driving cars.
Historically, the only way to tackle these was, well, one at a time. Each task had its own specialized, incredibly complex model. They were brittle, expensive.
And they couldn't really learn from each other. They were stuck in their own silos.
But today, we're doing a deep dive into a new paper that just blows that whole paradigm up. It's called Depth Anything 3, or DA3, from ByteDance and Seed.
And their whole approach is, well, it's shockingly minimal.
That's the perfect word for it. They want to unify almost all of these 3D vision tasks with an architecture that is just surprisingly simple.
Right. So, for you, the listener, our mission today is to really peel back the layers on this. How does DA3 pull off this magic trick? How does it get state of the art 3D reconstruction from, basically any visual input you give it?
Yeah, a single image, a bunch of pictures, a full video.
With or without camera info. And it does it with a simple, fast architecture.
And it's all built on this one core belief that depth, a really solid understanding of depth, is the absolute cornerstone for understanding the physical world.
For sure. The series started with just monocular depth, but DA3 is here to prove that a strong geometric foundation can basically solve any geometry problem.
So, to really get how big a deal this is, we have to look at what came before, right?
Definitely. Previous attempts at unifying these 3D tasks, they were complicated. People built these massive bespoke architectures.
Custom built for one specific combination of tasks.
Exactly. They were trying to optimize for, depth and pose and segmentation all at once, which led to these really engineered, complex solutions.
And DA3 just kind of looks at all that and says, hold my transformer. Their strategy is just so minimal. It really boils down to two key insights. First, they say you only need a single prediction target.
Right, this thing they call the depth ray representation.
We'll break that down in a second. But that first insight is it's a huge philosophical shift.
It is, because in typical multitask learning, you always run into this loss conflict.
Where improving one thing makes another thing worse.
Precisely. The math is literally pulling the model in different directions, and you often end up with just mediocre results across the board.
So by defining just one target, this depth ray DA3 just sidesteps that entire problem.
It cleans up the whole training process.
Okay, that's fascinating. So
Look,
simplifying the output simplifies everything else. What's the second big insight? The architecture itself.
the second insight is that a single plain off-the-shelf transformer is good enough.
You're kidding. No special modules.
Nope. They use vanilla Dino encoder. It's a vision transformer that's already been, massively pre-trained on huge sets of just regular monocular images. They're just leveraging the power that's already there.
But hold on. How does a standard transformer, which is used to seeing one image at a time, handle multiple views. Isn't that where things usually get really tricky?
That's the clever part. They use what they call an input adaptive cross-view self-attention mechanism.
Okay, say that again.
It's simpler than it sounds. Just think of the transformers layers in two groups. The first group of layers, they call them Ls for local.
Local, okay.
They apply attention within each image separately, just figuring out the features in image A, the features in image B, and so on.
Got it.
Then the next group of layers, LG, for global, that's where the magic happens. They alternate. First, attention within each image, then they reorder the data so the model can apply attention across the different views.
So we can actually compare a point in image A to that same point in image B.
That's it. It builds that geometric coherence. And they found a 2-to-1 ratio works best to local layers for every one global layer.
And the really elegant thing is, if you only give it one image,
The global part is just,
No.
it doesn't do anything. The model automatically becomes a monocular depth estimator. No wasted computation. It's incredibly efficient.
okay, let's dig into that core concept that makes this all work. The depth ray representation. This is how they get both scene structure and camera motion from one output. So what functionally are these rays?
Functionally, for every single pixel in an image, the model outputs a ray map. And this map defines two things for that pixel in 3D space. Its origin point, which is basically the camera's locator,
Camera center, okay.
and its direction, a vector pointing from that camera center out into the world through that specific pixel.
So you have the camera position, the direction it's looking for that pixel, and then the depth map tells you how far to go along that line.
You've got it. And that's the whole representation. It's like your camera has GPS and a perfect laser rangefinder on every pixel. The 3D point is just P equals origin plus depth direction.
Simple as that.
And that simple formula is enough to build the entire 3D scene and implicitly define how the camera is moving. The paper says it's way more stable than trying to predict 3D points directly.
So let's talk about the pose then. The camera's rotation and its internal properties, the intrinsics. I know predicting a rotation matrix directly is a nightmare for neural networks.
Oh, it's so hard. You have to enforce orthogonality, all these mathematical constraints. It's very difficult to train.
So if DA3 isn't predicting rotation directly, how does it get that information?
It uses the ray map as a sort of indirect clue.
Okay.
It already has the geometry right, so it can infer the camera parameters from that geometry. The camera center is easy. It's just the average of all the ray origins.
Okay, that makes sense.
Then for the hard parts, the rotation R and intrinsics K, they solve for something called a homography using a standard, very fast algorithm called DLT.
Direct linear transform.
Right. And once you have that, you can just decompose it into R and K using more linear algebra.
Mhm.
The key is these are classic stable math tricks. It's not a neural network guessing at the rotation matrix. It's mathematically deriving a perfect one from the geometry it already predicted.
That is so smart. The neural network does
From this podcast, I understand that what is the use of camera ray map and depth map. So camera ray map, as I said, it's giving the position for the pixels from the camera and the 3 prediction which is given from this model of depth, how far they are from the camera about each pixels. So they are using multiple images to construct a 3D of the any object or any monuments. So they are not using any neural network so to understand how these images are attached with each other. They are using model to predict the depth map and the camera ray map, and they are using mathematical expressions to attach, basically to stitch all those different images depth map. So by this they are able to create a 3D model. That's the interesting thing. It's help us, this notebook LM literally make easy to absorb the things. And let's see the video. Cool.
You know, for decades, we've been teaching computers how to see pictures. But seeing isn't the same as understanding, right? What if they could actually grasp the space, the depth, the 3D world locked inside those flat images? Well, a huge new breakthrough is doing just that, and you'll be surprised at how simple
The core idea really is. All right, so let's just jump right in with a question. How in the world can a computer take a totally flat, regular 2D photograph, something totally normal, like this shot of the Sydney Opera House, and then, poof, turn it into this, a rich, explorable 3D world? I mean, this is a point cloud, basically a map of 3D coordinates that you can fly through. And no, this is not science fiction. This is the incredible result of a brand new AI model.
So let's pull back the curtain and meet the wizard behind this magic. It's called Depth Anything 3, or DA3 for short.
Okay, so what is it? At its core, DA3 is an AI model that can pull 3D geometry out of, well, basically any of images. We're talking a single photo, a whole album of pictures, even a video. And here's the real kicker, the part that's just wild. It doesn't even need to know where the cameras were pointed from, it just figures it out. And trust me, the ambition here is absolutely massive. The researchers themselves put it perfectly in their paper. They said, depth is the cornerstone of understanding the physical world. So, you see, this isn't just about making some cool 3D models for a video game. This is about giving AI a genuine sense of spatial intelligence, kind of like the one we have. So, the big question is, how does it actually pull this off? Well, the secret is this really elegant philosophy the creators call minimal modeling. You see, for years, the standard approach was to build these super complex, specialized AI models for every single little 3D task. Minimal modeling completely flips that on its head. The whole idea is that a single, much simpler, unified architecture can actually be way more powerful. It's the classic less is more approach, but for AI. Okay, so insight number one from this philosophy, you don't need a huge, complicated toolbox stuffed with different models. All you need is a single, plain transformer. You know, the engine that powers pretty much all of modern AI. It's like having one of those incredible Swiss Army knives instead of lugging around a garage full of clunky, single purpose tools. The whole thing works. The model just takes in however many images you give it, feeds them all into this one single transformer, and that transformer is smart enough to share information between all the different views to build this coherent picture of the 3D space they all share. It's so clean, so efficient,
And it scales beautifully. Now,
So it's so cool. I will give this. I will upload this video, and it's very good though. And video is done, and the podcast, and okay, there is the slide deck. Am I pronouncing the word correctly? DECK. Okay. Let's see. Okay, this is the PPT one. Okay, depth anything recovering the visual space from any view. Okay, challenges our thesis. It can understand also transparent object because of their teacher and student model, where teacher learns the synthetic data, and they it's got trained on very clean data, and student got trained from the real world and the synthetic noisy and clear data. So they have literally made a perfect 3D model. Yes, that's cool. Crazy. Can you see, can you understand what could be the application in the video game world? It will be so, it can easily create the 3D world for us. So let's see this mind map, and here is the mind map, and we can see that is their core model architecture. We can see purpose, backbone, and okay, what is this then? Achievements. If I want to know the molecular depth, output da2. Okay, whatever the topics I'm clicking, it's giving, doing in chat also. Nice, so that I can understand the explanation and understand the this mind map. Cool. Nice. So for now, here is the end of this video. At the end, I would like to say, learn. Notebook LLM Notebook LM is available for us, and let's invest our time in learning so that we can get better in this world. Okay, bye.